Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the silo theorem, silo group theory, and in silo group theory we discuss the P groups. What is meant by P groups? In silo theory, we have to study the group action on a set, class equation of a group, and P group, and three silo theorem, first silo theorem, second silo theorem, and third silo theorem. Now we come towards the group action on a set. Group action on a set. Definition now see here. Let G be any group and X be any non-empty set. An action of G on X is a mapping F from X multiplies G to X, satisfying the following conditions. F of Xc is equal to X. F of X G1 G2 is equal to F of X G1 G2 for all X belongs to G and G1 G2 belongs to G. F of Xc is equal to X. F of X G1 G2 is equal to F of X G1 G2 for all X belongs to G and G1 G2 belongs to G. Under these conditions we say that X is a G set. X is a G set. Now every G set need not be a group. Every G set need not be a group. One should be noted. For example, a group action on a set. Let X is equal to a set from 1 to 3 n and G is equal to generated of Sn0. Define F from X multiplies G to X by F of X sigma is equal to sigma of X for all X belongs to X and sigma belongs to Sn. Then F of Xi is equal to I of X is equal to X, where I is equal to identity map defined on X. F of X sigma 1 multiply sigma 2 is equal to sigma 1 multiply sigma 2 of X is equal to sigma 2 of sigma 1 of X is equal to F of X sigma 1 into sigma 2. And from these two conditions, X is a G set. Now next example, one more example. Let G be any group and H is a subgroup of G. R denote the set of all right coset of H in G. Define F from R multiply S to R by F of Hx H is equal to Hx H. Then F of Hx is equal to Hx is equal to Hx, where I identity map defined on X. F of Hx H1 S2 is equal to Hx H1 S2 is equal to Hx H1 into S2 is equal to F of Hx H1 into H2. And this from these two conditions, R is a G set, H set. Now next example, one more example. G is any group and X be the set of all subgroup of G, define f from X multiply G to G by f of Tg is equal to G inverse Tg for all T belongs to X and G belongs to G. Then f of T is equal to E inverse T is equal to E T, and f of T G1 G2 is equal to G1 G2 inverse T G1 G2, G2 inverse G1 inverse T G1 G2, f of T G1 G2, and hence X is a G set. Next example, one more example for understanding. Let G be a group and H is a normal subgroup of G. Subgroup of G, only subgroup. Define a mapping F from G cross H to G by f of GH is equal to H inverse GH for all G belongs to G and H belongs to H. Then f of G is equal to E inverse G is equal to G. f of G H1 H2 is equal to H1 H2 inverse G H1 H2 is equal to H2 inverse H1 G H1 H2 is equal to f of G H1 H2. This is G is a H set. Next problem and for understanding, any group G is a G set under the action F from G cross G to G defined by f of G1 G2 is equal to G1 multiply G2 for all G1 G2 belongs to G. Let remark that let X be a G set, then by definition there exists a F from X cross G to X satisfying the conditions f of X is equal to X, f of X G1 G2 is equal to f of X G1 G2. Hence we write f of X is equal to Xg for all X belongs to X and G belongs to G. Thus X is equal to X and X G1 G2 is equal to X G1 G2. Let X be a G set for a fixed X belongs to X. Define Gx is equal to G belongs to G so that Xg is equal to X, and for a fixed G belongs to G define Xg is equal to X belongs to X so that Xg is equal to X. This is property of the Gx set we have to prove. Now there is a theorem. Let X be a G set for X belongs to X. Prove that Gx is a subgroup of G. This is nothing but we have to prove that it is sufficient to prove that X G inverse, that is G inverse, belongs to Gx and hence Gx is a subgroup of G. For this we suppose that X is equal to X, therefore E belongs to Gx, and provided that Gx is not empty. For G1 G2 belongs to G, X G1 is equal to X, X G2 is equal to X. Hence X G1 G2 is equal to X G1 G2 is equal to X G2 is equal to X. This shows that G1 G2 belongs to Gx. Now suppose that g belongs to gx, then xg is equal to x, xg, this implies that xg, g inverse is equal to xg inverse, xg, g inverse is equal to xg, g inverse. By associativity, g into g inverse is equal to e, therefore x multiply e is equal to x, g inverse. Therefore, x multiply e is equal to x. Therefore, x is equal to x g inverse. Hence, g belongs to gx. Therefore, g inverse belongs to gx. Therefore, gx is a subgroup of g. Now, one more definition there is. Let x be a g set. Let x be a g set. For any x belongs to x, the subgroup gx of g is called the isotropy subgroup of g. For suppose that x be a g set, for any x belongs to x, the subgroup gx of g is called the isotropy subgroup of g. Example for isotropy subgroup: let x is equal to 1 to 3, then x is a S3 set where S3 is equal to 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. The isotropy subgroup of 2 is 1, 1, 3. On each G set X, the subgroup G introduces an equivalence relations. These we have to prove in the following theorem. Let X be a G set. Define a relation equivalence on X by as X equivalence Y. This implies that X is equal to Y multiply G for some G belongs to G. Then the relation equivalence is an equivalence relation on X. Proof per proof, x is equal to x for all x belongs to x, therefore x equivalence to x is equal. Therefore, equivalence is a reflexive. Now, x in equivalence to y and x is equal to yg for some g belongs to g. X g inverse is equal to yg, g inverse is equal to yg, g inverse is equal to ye is equal to y. This shows that x is equivalent to y and y is equivalent to x. This shows that equivalence is symmetric. Now we have to prove that x equivalent to y, y equivalent to z. X is equal to y is g1, y is equal to z g1, g2 is equal to g1 is equal to z of g1 g2, g2 g1, as g1 g2 belongs to g, and we get x is equivalent to z, as x equivalent to y, y equivalent to z, x is equivalent to z. This implies that x equivalent to z for xyz belongs to x. Therefore, equivalence is transitive, as equivalence is symmetric, reflexive, and transitive. Therefore, equivalence is an equivalence relation on x. This is